Hi there and welcome to this iTunes U course on Senior Physics where we're looking at light and waves. In this video we're going to be looking at how to apply curved mirror formula. Now basically in the previous videos we learned that we can determine the position and the nature of an image just through an accurate drawing. But calculations have been found that can be applied so that we can calculate where the position of that image is and what the height is, and then using some of the aspects of the formulae, we can determine whether the image is real or virtual. Okay, so as I stated, we could use an accurate diagram to calculate the position and the height, but sometimes you'll get a question where it will say calculate. Now, the two key words that I always tell my students in class is that if it says measure, it requires you to draw an accurate diagram. If it asks you to calculate, then it requires you to use the formulae. Often what I've found in the past is that sometimes it says calculate and people do a drawing, and the word calculation requires you to use that formula. That's what we're testing. So be aware when you look at a question, if it says measure, you're going to be drawing an accurate diagram. If it says calculate, it's going to be using the formulae. However, be aware that you can do a rough sketch with your diagram just to double check your calculations. Okay, so what is the calculation that we use when we're dealing with curved mirrors? Okay, so we can basically work out with our formulae the distance that an image is likely to be from the mirror. We can also determine its height with a separate formulae, but they come from the same sort of area. Now the formula is a reciprocal formula or an inverse formula where you've got 1 over the focal point equals 1 over the distance of the object from the mirror plus 1 over the distance of the image from the mirror. So just to reiterate, F being the focal point, U being the object distance, and V being the image distance. Okay, now the key thing to understand is that they all are inverse, they all are 1 over. So when we do our calculation to find F, U, or V, you are going to have to do an inverse calculation as you're solving to actually find the value of U. Finding 1 over U, for example, will not give you the value of U. You'll see what I mean when we go through an example. But this is a flaw that I found a lot of students do. They do all their calculations and they get to a fraction at the end, and basically what they find is that 1 over U equals, for example, 3 over 2, and as a result they say that's what U equals. U equals 3 over 2, which is 1.5. That's not true, because basically U will equal 2 over 3, because we were dealing with 1 over U equals 3 over 2. So in order to find U, we have to flip both sides. We have to inverse both sides in order to get the calculation. That's where a lot of people have slipped up, especially when you're under pressure in the test. So be warned on that one. Now, another thing that we need to be aware of is the sign of the focal point. Now, basically, if the focal point is on the same side or the same reflective side of the mirror, hence it's real, then the focal point value is always a positive. However, if the focal point for a convex mirror is on the opposite side, so it's behind the mirror, then we show that as a negative. And what that means is that when your answer comes through, you will see whether your image is either a positive, being real, or negative, being a virtual image. So again, the calculation can help us tell us the nature of that image. So to recap, concave mirror, focal point is always a positive because it's on the same side of the reflective surface. For a convex mirror, the focal point is always on the opposite side. It's always behind the mirror on the dark side per se of the mirror, and hence is always a negative. Remember, focal point can be calculated by half the center of curvature. So we've got our equation which will allow us to calculate the distance of an image or an object from the mirror, and we also know how to deal with that formulae when we're dealing with either concave or convex mirrors. Those are all the things you need to actually understand to know in order to use that formulae. So it's very, very simple. Now, there is a second formula that will allow us to calculate the height of the image that has been used. Now, this calculation basically works on the principle that the height of the image and the height of the object is directly related to the distance of the object and the distance of the image from the mirror. So we use this formula m equals hi over ho, which also equals v over u. So m is what we call a scale factor. It's a ratio between the heights of the various objects, or a ratio of the distance of the object and the image. So obviously if the distance is halved, then the height will be halved. If the image distance is double the object distance, then the height is going to be double the object height. So as a result, m is only a scale factor and hence has no units. It's just a ratio between the height of the image and the object, or the distance of the image and the object. Now we can combine hi over ho equaling v over u, or we can utilize it in different ways. That's why I've put the formulae all together. So we might find the scale factor, we might not bother, we might just combine 3 out of the 4, hi, ho, v and u, to find our unknown. Okay, so let's have a look at a very, very simple example, and then further on in this post I've actually put some other examples for you to watch, and I've worked through them with a pen, and hopefully you'll find them quite useful. There are 3 worked examples there for you. Okay, so here's our example. So we've got an object of height 1 centimetre is placed 6 centimetres in front of a concave mirror of 4 centimetre focal length. We've got to find the position of the image and find the magnification and the height of the image. Okay, so question A, we've got to find the position of the image. So we know what f is, and we know what v is. We know what u is. So we use our formula, 1 over f equals 1 over v plus 1 over u. Remember, it doesn't matter which way we put the v's and the u's. Okay, we know that the focal point is 4 centimetres, so hence I can substitute in that second line. 1 over 4 for the focal length equals 1 over v, and I know the object distance, u, is 6 centimetres, so I get 1 over 4 equals 1 over v plus 1 over 6. So I take the 6th to the other side, so it becomes a negative. Now again, I've always found that people struggle with fractions, so be warned, the quarter is a positive there, so leave it as a positive and then put the 6th inside it. I always find it's easy to look like that. So on that third line you can see I've got a positive quarter minus a 6th equals 1 over v. So we find a common denominator, which is 24, so I get 6 over 24 minus 4 over 24 equals 1 over v. So 2 over 24 equals 1 over v. Now I have to inverse both sides because I don't want v being 2 over 24. It should be 24 over 2. So as a result, the distance of the image is going to be 12 centimetres in front of the mirror. Now note that the value there is a positive. Now because it's a positive, i.e. there's no sign in front of it, it means it's a real image. So it's going to be on the same side of the mirror. Okay, so we'll be able to put a screen there and actually get an actual image. Now, the next question asks us to find the magnification and the height of the image. So I use my formula m equals hi over ho, or the height of the image over the height of the object. Now I know the height of the object, okay, but I don't know my magnification factor. So what I'm going to do is use my values for v over u, and basically what we get is that the magnification factor will be the ratio between the distance of the image from the mirror, which is 12, and the distance of the object from the mirror, which is 6. So 12 divided by 6 is 2. So it's been increased in size by a factor of 2. So I now substitute that into m equals hi over ho, and then rearrange it so that I make hi the subject. So I get hi equals the magnification 2 times ho. Now I know HO is 1 centimetre because it tells me in the question. So HO is going to be magnification factor 2 times the height of the object 1. So my height of my image is 2 centimetres. So I hope you sort of understood the process. It's just a case now of just applying that formula each time and knowing what you're using. There are no other formulae that you need to use in this course. So really it's just a case of learning how to use it and manipulating it just to try and find the various things that you're asked for in your question. Okay, so what I'd like you to do, as I say, I've put together some simple and more complex mirror problems for you to watch so that you can then apply those techniques to various scenarios in the variety of questions that you're watching. Okay, well, I hope you found that useful, and I look forward to joining you again. Thank you for watching.